We are on MEE 362, Engineering Maths, Engineering Mathematics 4, Part 2, Numerical Analysis. This is our lecture 4. Let's go back to our book. Let's go back to our book. In this our book, we are focusing on certain methods. First, we have done a method of bisection. Now we are going to iteration method. I will also take Newton-Raphson method or Newton iteration method. So let's move to the page where we have the iteration method. Yeah. This is the iteration method. It's a very popular method and very effective. The method is introduced on this page, the iteration method. So if you have an equation and you want to find the root, make x the subject of the formula, you will have an initial guess value. What do I call it? Initial guess value. Again, what do I call it? Initial guess value. So you are going to say the root is x equal to x naught. You are going to substitute in that expression. You are going to get another value. When you get this value x1, you know your x naught is a guesswork. We call it initial guess. So when you substitute x naught in the function, you are going to get x1. What you do now is that you substitute x1 into the same function. You are going to get x2. So resubstitute x2, you are going to get x3. Resubstitute x3, you are going to get x4. You continue like that. As you continue, your x1, x2, x3, x4, xn will be approaching the exact root that we are looking for. It's saying where the sequence of approximations x1, x2, up to xn will convert to the root. He said it can be shown. We're not interested in showing, please. We just want to master the method. We just want to master the method. But the theorem is there. We don't need to memorize it. Let's dive into an example. We are going for the first example. It's saying certain things. Iteration method is more useful for finding the real roots of an equation, which is the form of an infinite series. Find the root of our first example. Find the root of x3, x raised to power 3 plus x minus 1 equals 0 by iteration method. Given that the root lies near 1, which means you use 1 as your first approximate value. You use 1 as your first approximate value. So make x the subject of the formula. You can say that so if we say that let's see what he did here. I think he pushed 1 to this side. He pushed 1 to this side, and he has x raised to power 3 plus x. Factorize, bring x out. So that would be x into x squared plus 1. And then you can take x squared plus 1 to the other side. So please, this expression is formed from here. This expression is formed from here. So what the next thing you are going to do, is to now your guess value. If x naught is your x naught equals 1 is your guess value, put 1 here. If you put 1 here, what are you going to get? So what are you going to get? If you put 1 here, this will be 1. That will be 1 over 2. That will be 0.5. So so this is the first x naught is the guess value. We do the first iteration. We substitute x naught equals 1. We're going to get 0.5. Now the same expression, bring that 0.5 here. We are going to get x2. Bring that 0.5, then you get 0.8. Bring 0.8, you are going to get 0.61. The root of the given equation is 0.61 after 3 iterations. We can continue. By the time we continue, we see that the answer will try to converge. By tomorrow, I'm going to write a program that will calculate it, but on your own, you are not using programming. You have to calculate. On your own, calculate x4 now. How do you get x4? Bring 0.61 here. You get x4. When you get x4, whatever x4 you get, bring it here. You continue. At least before tomorrow, let each of you try to get like 20 values. You will see that your value will be converging to a particular point. So on my own, I'm going to write a MATLAB program that will resolve this. But you are going to be calculating as students. So this is the iteration method. If you write a program to do the computation, you need to be able to stop. You cannot continue the iteration indefinitely. You must have criteria to stop. For example, if you are interested in 2 decimal place, correct to this 2 decimal place. Once you realize that 2 decimal places are becoming constant, you did x5. Now this x3, we did x3, we got 0.61. If we do x4, we still get 0.61. We do x5, we still get 0.61. There will be differences in the 3rd decimal place, 4th decimal place. So if you're interested in 2 decimal places, then you are going to stop the iteration. If you are interested in accuracy to 10 decimal places, you may have to do the iteration 500 times, 400 times. So when you draw a program to do this, you have to put a condition to stop the iteration. You must know where to stop. So it depends on the degree of accuracy that you need. If you need to be accurate to 4 decimal places, you do more iterations than when you need 2 decimal places, and so on and so forth. I hope that is clear. So this is the first example on iteration. Dear students, example 2.6 done. I hope you know the meaning. Go and do example 2.6 on your own. Follow the way it is done here. You can see this one. You can look at this. By the time they calculate x6, 0.60709, x7, 0.60710, x8, 0.60710. You see that there is not much difference as far as 4 decimal place is concerned. Even here, if you approximate this to 4 decimal place, it's still going to be 0.6071. 0.6071. We can stop there because it is now correct to 4 decimal places. But if you want correction to more decimal places, you have to continue. Exam 2.7 done. That means go and follow it on your own. Example 2.8 done. Go and follow it on your own. You can see here, they got 1.434. This is also 1.434. This 1.442. So which means if you are looking for correct to two decimal places, we have gotten it. From x5 is 1.43, x is 1.43, x7 1.44, x8 1.44, which means we are now on two decimal places. And this other method, let us keep it. Delta square method, let us keep it. We are not studying all the methods. Our time will not permit us to be able to study all the methods. Outside the class, you can study it. So don't bother about example 2.9, but you can use the method we studied to solve it and compare the result with what they have here. All the examples under this method, you can use the method that we know to solve it. So that brings us to exercise 2.3. I'm going to give us some assignment there. Sorry, I've changed the assignment. It will not be together at the end of my part. I will be doing it gradually. So this brings us to what is called Newton-Raphson method, or Newton iteration method, or Newton iteration method. Well, let us not bother about how they arrive at the method. Let us master the method. The method is summarized here. The method is summarized here. The method is summarized on equation 12. How do you use this? Let Xn be your current iteration. It's still an iteration method. If Xn is your current iteration method, iteration root, you are going to find f of Xn. And you are going to differentiate the function f. So you are going to find f prime of Xn. Then you are going to Xn minus fxn divided by f prime xn. That will be your next value. That will be your next value. That will be your next value. An example will convince us. So please master this, or you may have to memorize it, but by the time you start using it, you don't need to memorize it. It will become part of you. It will be at your fingertip. This is the formula for Newton-Raphson method, or Newton iteration method. Let's go straight to an example. Let's go straight to an example. Let's go straight to an example. Criterion for ending the iteration. The decision of stopping the iteration depends on the accuracy desired by the user. If epsilon denotes the tolerable error, then the process of iteration should be terminated when xn plus 1 minus xn is less or equal to epsilon. Xn is the previous result, the result of the previous iteration. Xn plus 1 is the result of the current iteration. So if the difference is less than this, then you can stop. So let's discuss example 2.10. Using Newton-Raphson method, find correct to 4 decimal the root between 0 and 1 of the equation. Since you are told that there's a root between 0 and 1, I think what you can do is that you can guess any value to start with. You can guess any value to start with. Now, first, this is a function you are given. You have to differentiate it. When you differentiate it, x cubed become 3x squared. Minus 6x become minus 6. So this is the f prime, that is f. So let our x naught, just guess. When you, ladies and gentlemen, repeat this problem, start with x naught equals to 0.5. Let's see if you are going to arrive at the same results. You should arrive at the same result anyway at the end. Now, so please, let each group redo this example 2.10, change x naught to whatever you like. Let it not be 0.7. Let it not be 0.7. So that's a group assignment. Let's join it with the one that you are doing currently. So this example 2.10, course rep, let me write it down that the second assignment is that example 2.10 should be repeated. Use another value for x naught. Let the value be between 0 and 1. But in this example, they are using 0.7. Let us follow them. So in this method, the function you are giving, you are going to write it down. You are going to generate the differential like that. Now let's compute fx naught. Fx naught. Put 0.7 in this expression. What do you get? You are getting 0.143. So that is the f. You see this formula? We need f of x naught. We also need f prime. So put x naught in this case. Here they make a mistake. They wrote f prime x naught, f prime 0.7. There's supposed to be an equal sign here. They mean that f prime x naught is equal to f prime 0.7. That means x naught is 0.7. When you substitute 0.7, you are going to get this. Now, to get the next result, use this formula. Substitute for x naught, which is 0.7, which is 0.7, which is 0.7. Substitute for f prime x naught, which is minus 4.53. Then you compute that. You are going to have 0.7316. We are going to use this our x1. You know, we started with x naught. You will get x1. The next is that we are going to look for x2 now. So for x1, we are going to repeat this. Substitute, instead of substituting, you know, we substituted x naught before. Now substitute x1 here. That's what they are doing here. We are going to get this. In the f prime 2, substitute x1. And then adjust your formula. You know your formula is saying x1, x naught. Your formula will now be saying x2, x1. You get it? The formula will now be saying x2 equals x1 minus fx1 over f prime x1. I hope you see the way it is progressing. Okay, what will be next after this? It will be x3 equals x2 minus fx2 over f prime x2. The next will be what? x4 equals x3 minus fx3 over f prime x3. So you compute x2. This is your x2. It's stopping here. I think it is correct to how many? To 4 decimal places. But if I were you, should not stop here. Do up to x3, x4. If it is not more than this, if we don't, if for example, when you get the next one and you got 0.7321, and you get 0.73212, that means to see that amount. If I were you, I would do 2 more. I'll be convinced that 4 decimal places is no more changing. Please, example 2.11. Example 2.11. Done. That means go and follow it on your own. Example 2.12. Done. That means go and follow it on your own. Please, practice makes perfect. You cannot understand a topic until you practice, 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 practice. So I think this chapter 2, we have come to the end of this chapter 2. We have learned about 4 methods. Is it 4? We started with graphical method. We mentioned bisection method. We mentioned iteration method. And we mentioned the Newton-Raphson iteration method or Newton iteration method. I will do something. These methods, I'm going to write programs that will execute some of these tasks, and I'm going to upload it in the Google Classroom. I think we can stop here. Please, ladies and gentlemen, make sure as you watch this video, make sure you jot, make sure you move along. Out of the 3 weeks allocated to me, we have completed 1 week already. So let us stop here. Let me stop sharing first. Let me return you to the page. So thank you for having me. I hope everybody will be up and doing on this course. I wish us all the best. Good night.